This talk is all about how we at Intel are using the Linux UEFI Validation project to test our kernel and firmware changes. And the LUV project was started in January 2014 as a kind of grassroots project to address a gap in the testing coverage that was happening at the time. Being the kernel maintainer for EFI, I saw a lot of bugs coming through that really should have been caught earlier on when the firmware was being developed, and the same kinds of bugs kept cropping up. And the problem was that people writing the firmware really didn't have this pre-packaged solution for testing Linux. And so we thought, well, let's create a distribution using the Yocto project, whose sole purpose is just to do the testing of the kernel and firmware interfaces. So that's what we did. We packaged together different test suites into a single distribution to try and provide cross coverage for both the boot time and the runtime, which nobody was providing at that point. You had test suites for the boot time and test suites for the runtime, but there was nobody doing both at the same time, and there was nothing that linked these two separate phases of boot. And so the first question that people ask when you tell them that you created a brand new Linux distribution was, do we not already have enough? Why can't you use Ubuntu or Fedora or something else? And the reason is that we wanted, the mission of the distribution was the complete opposite of any standard Linux distro. So most distros want to turn on all hardware support, turn off all debug features, and be as performant as possible to provide a nice user experience. And we wanted the exact opposite of that. Turn on every single debug feature, turn off performance stuff, crash as fast and as hard as you possibly can, and then gracefully recover to provide it's kind of like a black box, a flight recorder style thing. So anything that happened up until the point you crashed, you need to record all of that so you can analyze it later offline and figure out why you crashed and fix that bug. So that's what we did. We created a distribution with this sole intention. And very simply, it's an umbrella project. It's just a packaging of existing open source projects. We don't write our own tests. We add to the existing tests, fix bugs or add new features, but we don't create a brand new test suite. What we do is, kind of following the example set by a lot of the Linux distributions, we just provide a USB flash image that you can put on a USB pen. And that was really pretty useful to address the very first problem we had with the project. Was basically, okay, we've got this idea, we think this makes a lot of sense, it would save us a lot of work if people ran it. How do we get people to run it? And so the first solution was, well, USB drive. It's easy. Hand out the plug fests, that's all done. But when people started using it and running into bugs both in the firmware and in the kernel and in the test suites and actually in the distribution, so in the glue that ties all the test suites together, trying to go from those bugs to solutions using the USB image is it's super difficult. Especially when people are reporting problems to you on hardware you don't have across huge geographical distances. And so I refer to this as the 5,000-mile problem, because from where I'm sat in my home office in West Yorkshire, the Intel labs that house some test machines and things we've bought that are off the shelf that we test Linux on, it's about 5,000 miles, and that distance became a huge problem for the next phase of the project. You can't ask people to run down the hall with new versions of a flash image and plug it into the machines. Well, you can, but twice. And people start dodging your phone calls and not replying to your emails. So we needed some way to overcome this barrier because the USB images, frankly, they just don't scale across geography. It's a good initial solution, a good solution if you're sat at the testing machine, like at the plug fests. But beyond that, it really isn't. It's not useful. It's really difficult to get that to work, and trying to debug problems via other people using the USB images is just it's painful, because not everybody that reports bugs is a kernel developer or a firmware developer. Some people are QA guys, and the value they're providing to your project is just reporting the bug in the first place, which is great. We love that. We want bug reports. But the person doing the reporting is not always the person that can address, provide the solution, address the problem. And so what we did was we leveraged the existing BuildBot infrastructure. So the BuildBot's a Python project that is a continuous integration framework. So very similar to Yocto, it just provides you with some tools and you build your continuous integration system from the tools. So we took that and we started adding little pieces on top of it to fit our specific need at the labs at Intel, because we've got a mixture of physical and virtual machines. OVMF is awesome, so we use QEMU and OVMF to write a lot of the kernel code, because sometimes that is the first or the easiest platform that we can use to do that. And we try to version control everything, because if you're really going to go for the automation, the overcoming these geographical distances, version controlling is key. So you can roll things back when you have bugs and roll things forward, and just keep track of what's going on as you try and scale out. So if you go to the BuildBot website, this is the diagram that you'll see. It's very generic, very high level. It just shows how you can monitor repositories where your project is contained, pull the changes down as they appear, and then do some compilation or some kind of stuff. And then you get status updates. But this isn't really very useful to our discussions, so to make it a little more concrete, this is what things look like for the LUV Shack. So all of the LUV projects, that's the distribution, is in GitHub. Everything's there, all the commit history is there. And we just monitor changes to the branches in that repository. When we find new changes, we pull them down, build a distribution image with those changes, and then start using that to push out to the test machines. And then we've got cool status hooks. So we have the standard web interface that BuildBot provides is pretty cool, actually. I've got a bigger diagram later. But we also have IRC hooks, so you get notifications when you're sat in your IRC client when the build breaks. So if we pan to the left and kind of zoom out a bit, or zoom in actually, this is kind of how things are structured in GitHub. We just use the concept of a Git branch as a playground for new configurations. So the branches in GitHub for the LUV project, it's kind of all just metadata. So in those branches, you point further out to projects, to different versions of projects. So a good example of this is when you're writing kernel support for some new feature, which I've got a case study in a couple of slides. When you're writing kernel support, you will, at the very furthest level, point to a kernel.org branch with those kernel patches. Everything else may be totally standard, apart from the kernel patches, which are different. So because the middle layer is just metadata, it's all very standard with how you build the images. All the quirks, all the differences are taken care of using the middle tier and the metadata. And because almost everybody uses Git, like everything's a Git branch, so it's very easy just to start switching stuff around. So doing the hard part about writing the kernel patches is writing the kernel patches. It's not doing the building or the integration work. That's about 20 seconds worth of work, which is how it should be. I mean, the kernel patch is the hard part. Actually pulling stuff down, building it into an image and running it, that should literally be like a couple of keystrokes. And so using this paradigm, this design, that's exactly what we get. By the way, if anybody's got any questions, please just shout out as we go through. Yeah, don't read this. At a very high level, the intention of this slide is just to show how few lines of code you need to add specific stuff for your project to BuildBot. And there's like 3 commands. So it's where's the repository, what branch, run the build script, because most people have got build scripts. But that itself is only a few lines because it uses the Yocto project. it's just a bit command and then pointing at the config file. So it's a couple of lines. And then kick off the tests. And the trigger is probably the most interesting part of the whole thing, because building stuff's just easy. People have done that for ages. But the testing and the triggering which platforms to run tests on, that's the more interesting piece. But BuildBot provides hooks for all of that. And so there's documentation for doing this exact style of thing, because everybody wants to do this. And so using this framework, it becomes super trivial to wire all this stuff up. Yeah. So this is kind of like a logical overview of the other part of the original diagram, which is the testing. So you've found some changes, pull stuff down, build some images, and now you want to push things out onto your testing machines and test things out. And we have this mixture of virtual and physical machines. We net boot some of the machines. So right now I think we're net booting some of the Minnow boards, which is super useful. That's a really cool way to do it. But also the using the virtualization, because that's all part of Tiana Core, it's super easy to to wire up changes in Tiana Core into the test system. And we've got stuff like we build OVMF with secure boot enabled, so we test secure boot and then non-secure boot. And then we have like the SDVs, like the tunnel mounted machines, and then the older strawberry mounted stuff. That's all part of the LUV Shack, because we can just net boot that stuff and then run the tests and then grab the results. So this is what I spoke about earlier. Grabbing the results is kind of the entire point of the process, and the default BuildBot interface is really quite neat for providing that high-level description of how your project's going right now. So every one of these columns on the right is a description of platform and let's call it config. And exactly what's in that config varies. So you would have a column for running your new kernel patches. The kernel patches being the only difference from the standard LUV distribution on OVMF and then the tunnel mountain platforms and stuff like that. And then you have different architectures as well. So we've got support. We build for ARM64. And the reason for that is we kept breaking it. And Naresh, who was working on it, he's a really nice guy and he didn't complain, but I could just kind of, he almost complained. He was getting to that point where he's thinking every week he's sending emails saying, guys, you broke this again. I think, that guy's so polite. I'd have been screaming by this point. So now we build for ARM64, but again, that was one person worked on it for half a day or something, maybe 1 day. It was a very straightforward change just to wire that up. And, yeah.
You might get to this later. So how do you actually wire this up? How do you extract the individual test results from the test bar?
Yeah, so it depends which machine it's on. So for the virtualization stuff, we just write to a file on the host. Whenever we're running the VM, write to a file and pull the results out of the file. And then we've got parsing, to detect changes, if you regress with a certain result. And then for the net boot side, I'm going to choose my words carefully because this is kind of work in progress. This is like cutting edge stuff that we've just done. I think it's pulled across. It's stored on the TFTP server. I think.
Kind of
push,
local disk, and then you're sending it across.
Yeah, I think so. Yeah, because I mean, it's just text files. They're not huge, and what you're really doing the digging of why things have gone wrong requires a manual intervention, I guess. But like for regression checking, you get that instantaneously because you know when things have changed. Because you can send this high level, because the stuff on the left is just straight out of the file, and then so you get that, this now passes and it shouldn't have done. Why has it started passing? And sometimes that's good, and sometimes that's bad, like it shouldn't be passing, So yeah, it depends on which platform you're on, and we do a couple of different stuff. But for the USB images, so for the historical way, we just start on the USB drive. And for a lot of scenarios, when geography is not a problem, that works pretty well. We've just merged support for multiple result files. So it used to be the case that if you plugged in the USB image and rebooted a couple of times and ran the test, you just squash your results, it works, but if you're going to different machines, you kind of want to, you may want to aggregate the results across all the machines you can run on, so now we have different directories for different test runs. Yeah, so we found that by really kind of chasing this automation, we could do a lot more stuff really quickly. Running tests in parallel, debugging issues remotely is the main one, and trying to avoid that vicarious debugging. If people are okay with that, I'm game, I'll do that. But sometimes people have just got no interest in pulling down version after version of new live images. They're like, I think they're about 80 meg. So it's not tiny, it's not huge, but it's certainly a burden to ask people to, I've tweaked this thing, please flash this again and run it again and send me the results back. So being able to overcome that has been a great benefit to the project. And now we can, sorry, yeah, go ahead.
Just on that exact issue, when you've got a problem that exhibits only on one remote system, what's your mechanism for pushing that link just to that one and dragging it back? How does that all integrate with
So that's done at the buildbot config, because you have to tell buildbots what you want to run where. So you create that initially, so that initial config, and then when you run the test, you see if things are bust or not, and then
So buildbot gets to schedule the job and choose when to run it rather than
yes,
things autonomously running and then reporting back.
Yeah, it's the first one. So part of buildbot, one of the main features of buildbot is a job scheduler, and it does a pretty good job of that. So. Yeah, so because it's getting easier to add more machines as so every machine you add, it gets a little bit easier because you start wiring up stuff that's the same and sharing pieces of code. The whole project is probably a couple of hundred lines of Python and a bit of Bash. It's not a huge amount of stuff because the magic really, I would say, but I'm biased, the magic is really in the LUV project, and pulling all these tests together and then gluing the separate test results into a coherent thing. The rest is just Python. And it's been really cool. So I've used this extensively for testing kernel patches. This has really been where the itch I was trying to scratch was testing of kernel changes with firmware. And so, as I mentioned earlier to Leif, you can track how things are changing over time. And buildbot does this actually. So buildbot maintains like a database. I think it's a SQL database or something. So you can see how the results are changing, going back weeks and however long you keep the database for, which is good because it does allow you. It's a fallacy to think that things pass all the time. Sometimes things do fail, and you're like, well, I know that's bust, but I just can't get to that right now. I'll come back to that one. And so having that track record of how long has it been bust is pretty useful for discussions. Like, please go fix this. It's been bust for 2 weeks. Everything about the project, about the team working on the project, just runs faster now because you don't have these awkward emails like, hey Ricardo, please go down to the lab and power cycle that machine. You just skip all that. So I can do that remotely. And because you can do this sort of stuff, as you start tackling these issues, the scope of your problem just gets bigger and bigger. So the first problem we had with the project back in 2014 was, this is neat, but how do we get people to run it? So we thought, USB image, awesome. And then we had all the problems with the USB image, like, well, this guy in North America sent you an email last night, Matt, and it's posted on his machine, and none of us have that machine. Okay, well, can we get one? Yes. Can we all get one? No. No. Get one. Okay. So you put that in a lab. So then you can run stuff on remote machines. So just getting the machine now solves that problem. Everybody can connect. Everybody can run their own tests because the job scheduler takes care of the arbitration. Who gets to run what when. So we did the remote thing, and then we thought, well, this is cool. So how far can we push this? Like, well, we all like Git, so let's just start creating Git branches for everything and testing out random stuff on machines, because it's just like a single line change in one of the Yocto project configs. We'll make a Git branch for that, push the Git branch, and then all this magical stuff, all the layers of indirection, just get you like a multiplier of your effort. Okay, so that was kind of high level, certainly in terms of use cases. With the EFI properties tables change in the UEFI 2.5 spec, if anybody's been monitoring the list recently, there has been some issues with the implementation and the interaction with certain versions of Linux. On the x86 side, it was anything newer than the 3.13 kernel. If you turned on this feature in the firmware, it didn't run. And for the ARM64 side, was that version specific, or just did it start breaking at a certain kernel version, or was it just?
Well, we did it overall at 4.0, but it's most likely broken before that as well, because we had the rounding there.
Okay, so since the support was merged, probably.
Yes.
Okay, so this has always been broken on ARM64, and we talked about this, and we did the usual UEFI Forum thing. We had meetings about it, and everybody knew it was a problem, it was a gap, and we needed to fix it up. On the LUV team, we had this unusual problem where we didn't actually have hardware with this feature enabled. And so what we did was create a new Yocto branch and use OVMF. So thanks to Ard, we stole one of his, reused one of his Git branches that very kindly wired up this feature for OVMF, which nobody had done until that point. And so there was, how many was that? 5 commits. 5 commits, I think they're all one-line changes to go from having no hardware support, no ability to test this, to debug it. So that's like 60 seconds worth of changes there, although I think they might have been split across a couple of days. And going from nothing to 5 lines of Python and Bash, and then we had a virtualization solution to start testing this stuff, which is much more useful because then we could have meaningful discussions about exactly why it broke, under what conditions it broke, and then we could go about fixing it, right? So we started proposing solutions for this, and that's what we've been working on in the UEFI Forum, in the meetings, to try and get this resolved. There are now patches merged that fix this problem, so it's not a problem. It's not a problem now if you have the patch. Whether or not you have the patch in your distribution is like another concern, but we'll get to that later. Yeah, there's some work still to do for that. So, how am I doing for time? Did I burn for that pretty fast? Okay. Yeah, pretty fast. Okay. Yeah, so final things I want to talk about really are that please, whichever option you pick, just start running the LUV project. If you have, I know there have been cases of people running it and hitting problems in the distribution, so our bugs, and then they just didn't tell us about it. We don't have telemetrics that actually might be coming. So when you do that, we have no idea that's happened. If you try it out and you hit a problem, just send me an abusive email, and I will happily get things working for you. Whichever one of these you pick, if you want to start experimenting with wiring up in your existing validation infrastructure, or you want to create something from scratch, I think what we've shown with the BuildBot stuff is that it's pretty straightforward to go from having no automated validation to having something that works pretty well just by having the LUV project at the center of that. All the magic is in the middle, and the other stuff is just kind of glue. So if you're interested in doing that, please let us know if you have problems, or if you don't, if you just want to say, yeah, we did that, I would love to hear about that. if you just want to start tinkering with stuff, QEMU is a great way to start doing this. I still use it. I've written most of the kernel features I've written for EFI, I wrote using QEMU. So it's totally production ready, I think is probably the phrase. So the other side of this is, if you're somebody who writes tests and we don't include your test in LUV, I would love to add it. Please let me know, because we were never. The project has never been intended to supplant anybody's efforts or projects or programs. We just want to be an umbrella. We just want to grab everything we can and run all of it. We've started trying to wire up the UEFI Forum's SCT, the self-certification test. And there's nothing. So what one of the really cool things that happened, I think it was last year, is they started publishing SHA checksums for the files, which is a really nice move. In part because you get that kind of, if you're trying to do certification, you get that authenticity check that what you're downloading is what you intended to download. But also the Octo project requires it. You have to point to, you have to give a checksum for the files you're downloading. So we've started working on the UEFI SCT integration, but we'd love to add more. If you've got ideas for testing, maybe you haven't written something, tell us about that. If you found a bug that we don't test for, please let us know about that. This one's a long shot, but I probably never get a better audience to ask this of. So if you're making changes to the spec and you think, I know how I could test this, I've got a really cool test, but I don't have the time to write it, I'm not sure how to write it. I'd love to start that discussion, and we could probably do that. Write the test for you, depending on how, how big it was, because that's never happened as far as I'm aware. Nobody's ever, and I'm not talking about releasing the test necessarily before the spec. How you want to order stuff is fine, but we have stuff in the spec that has no tests, especially at runtime from the OS, which is obviously where my focus is. But getting that communication between the two is vital, and really the testing is the only way that I think to do that. You have to have sufficient tests at all stages to ensure that what you think the OS is doing is actually what it's doing. It's true with the firmware as well. We in Linux have been guilty of making certain assumptions about how about the way the firmware works that have turned out not to be true. It basically boils down to a communication issue. You've got two different camps doing this. So testing is the way to bridge that gap, at least in my opinion. And yeah, it's definitely, if you want to use LUV in new crazy ways, I'd be happy to support you with that and help you out. So these are just some links to the various bits if you're interested in BuildBot, which is a very cool project actually. That's a good tutorial there. It's about 5 minutes, just to breeze through that. And there's projects for LUV. There's links for the LUV project, and then the Octo project is. I would be remiss if I didn't include it because we have leveraged that a lot. Those guys do some great work.